My geometry class. I'm Dr. Mason. Now, we won't really begin the class today, the necessary work of the class. Instead, I thought I would simply talk about the structure of this class, what we do in this class, because I know it's different. I know that you know that it's different than any class that you've had before. You've been in algebra classes and before that pre-algebra, and then you've done arithmetic, of course. So you're familiar with that kind of work, but now you're in a geometry class, and perhaps you have heard that this is a proof class, and that is certainly true. And I would not be surprised if you had a little trepidation about that. So I thought that before we actually launch into the content of this class, which we will do next time, instead I would just talk a little bit about what we're up to in this class, which really means we have to talk about the structure of the work that we do in this class. And I'll do that with the help of that great ancient Greek mathematician, Euclid. So let's talk through this quickly. So, like I said, I know that you know that this is unlike any mathematics class that you've taken before, but do not panic. As Douglas Adams famously said, I know you can do it. And how do I know that you can do it? Well, I discovered over a decade ago that students in your position, students of your age with your background, can do what is doing that we do in this class because I have seen them do it year after year. So though you do not have the skills at this moment in time that you will have by the end of the year, if you do what I ask you to do, you will absolutely have those skills. So just work with me. We'll get there. What do we do in this class? Well, geometry, of course, you knew that. You knew that. That means, of course, that we study objects like points and lines and angles and polygons and circles and all the rest. But from my point of view, that's really not the best answer to the question what we do in this class. It's not false, of course. That's those are the objects of study in this class, but that really doesn't get at the method of this class. So what like to talk about a little bit here is the method of the class. So what's most important is that we're system builders. We build a mathematical system, the system of basic geometry. Well, what does that mean? What does it mean to build a mathematical system? Well, to really know, you'll have to build the system with me. So you'll learn that as we work our way through the class. But I think I can, at this moment in time, give you a rough sense of what it means to build a mathematical system. And to do that, we'll go back to Euclid, Master Euclid, as I'll often call him. Let me talk to you a little bit about Euclid's great work of geometry. It's called The Elements of Geometry. Euclid was the ancient Greek master of geometry. The Elements was his geometrical masterpiece, and it's now about 2,300 years old. Think about that for just a moment. 2,300 years old, over 2 millennia old. By the time of Christ, this was already quite old, centuries old. Most of the work that we do in this class will be drawn from Euclid's Elements. So, though certainly mathematics has progressed past Euclid's Elements, nothing in the Elements is incorrect. Indeed, it's still the foundation of geometry. So, we'll do basically Euclid's Elements in this class or a version of it. Now, what is the structure of Euclid's Elements? Well, to answer that question, side point, since we followed Euclid's Elements, the structure of the elements will be the same as the structure of our class. Now, to answer that question, what is the structure of the elements? We have to make a three-part distinction between statements that are definitions, statements that are postulates, and statements that are theorems. Of course, Euclid's Elements is composed of mathematical statements, one after the next, but ultimately all of them are definitions, postulates, or theorems. And we'll be able to use this three-part distinction to make sense of or to describe the structure of Euclid's elements. So let's talk a little bit about the structure, about what these three are, and then we'll experience what the structure of Euclid's elements is based upon them, which again will be the structure of our class. So a definition tells us precisely when a term or phrase applies and when it does not. That is, we'll have certain technical terms in this class, perhaps not highly technical, but certainly technical in the sense that they belong in the mathematical classroom. Like, for instance, I don't know, polygon and, I don't know, complementary or something like that. And we'll have to say when these terms apply and when they do not apply. And that, of course, is the definition. Here's an example. Euclid's definition of isosceles triangle, which by the way, differs slightly from the definition that we will offer of isosceles triangle later on in the class. But what Euclid says is that an isosceles triangle has two and only two equal sides. What this means, of course, is that if we know the side lengths of a triangle, we know whether the word isosceles applies or not. So there's your technical term, isosceles, and the definition tells us when the term applies and when it does not apply. We'll have much more to say about definitions in the future, but that's our first example. Now, the second kind of statement that you find in Euclid's Elements is a postulate. So after definition comes postulate. Now, the notion of a postulate is more complex than that of a definition, and we'll have much to say about it throughout the course of the year. And indeed, I don't think we'll really understand it deeply and well until the course is done, but we can say a little bit about what we mean by postulate right now. Postulate is a basic assumption, where by basic we mean unproven. And here's one of Euclid's postulates, and on the assignment for today, you'll see others as well. Things equal to the same are equal to one another. Now, take just a moment to think about that so you'll understand what it means. Things equal to the same thing, I should perhaps say, are equal to one another. That does seem true, doesn't it? So, for instance, if, well, we can use some variables here. If A is equal to C and B is equal to C, that is, we have two things A and B, both equal to a third thing, C, then it follows that, of course, A and B are equal to one another. So that's one of Euclid's postulates, and it will be one of our postulates as well. It's extremely important, and it will serve for us as a basic assumption, which I think is perfectly fine because it seems to me that this is obviously true. Now, theorem. And this really is the most important of the three for us, at least if we judge by the amount of time that we'll spend on it in this class. A theorem, also called by Euclid a proposition, is a statement that's been proven true. Proven how? Well, that means that it's been derived from definitions, postulates, and previously proven theorems, if we have any of those. Now, of course, the obvious question at this point is, what does derived from mean? Well, we're not ready for an answer yet, but I think you'll have some rough sense of what it means. We'll start with definitions and postulates, and then from them we will be able to derive what we call our theorems. And here's a famous theorem for you, one that we will actually prove later on in the class in the second semester. In a right triangle, the sum of the squares of the legs equals the square of the hypotenuse. You will probably know this is the Pythagorean theorem, and we will prove this later on. We will show how this can be derived from the postulates and the definitions that we will offer. Now, with all of this said, we can, I think, describe the structure of Euclid's Elements, and so answer the question what it means when we say that it's a mathematical system. Well, when we say that Euclid's Elements is a mathematical system, we mean that it's one in which we prove every statement that is not a definition or a postulate. That is, as Euclid will do, as you'll see that Euclid will do, we will state our definitions and our postulates, and then the primary work of the class, we will prove on their basis the theorems of the class. And that process of proof where we derive from our definitions and our postulate, that's what binds together the statements of the class. And that's what then makes it a system. Okay, so what makes it a mathematical system is proof. When we give proof, we bind the statements together. We show how they can be derived from definitions and postulates. And so we make it a single unified structure. That's what we're really up to in this class. Okay, yes, of course, we study geometrical objects like points and lines and triangles and circles and all the rest. But what's really more important is how it is that we study them. That is, we define our technical terms, and then we state our basic postulates, which will be fairly few in number. And then from that, we will derive all the other statements of the class, which we will then call theorems. That's the basic structure of what we do in this class. We are provers. We are theorem provers. Now, with that, I think I'll leave off our discussion of the structure of the class. And we are certainly not ready to give our first proofs yet. We have quite a bit of work to do before we reach that point. Indeed, we won't be ready to prove our first theorems until chapter 3. But tomorrow we will certainly begin the process that will lead up to the proofs of our first theorems. And just like Euclid, we will have to start with a set of definitions. So mostly what happens in this chapter is we give definitions. Now we also learn how to draw diagrams for objects of certain typical sorts, and we'll learn how to label those diagrams as well. But primarily what we do is we learn about the basic objects of this class. And then in the next chapter, we begin to discuss what it means to derive from. And then by chapter 3, we're able to give our first proofs.